Next topic we'll discuss is the thermodynamic process. So when a system undergoes a change from one equilibrium state to another equilibrium state, then it is called a process. So suppose you have one system, initially it is at some equilibrium state. Now by some external influence this equilibrium state is disturbed. Okay, then it will settle for a new equilibrium state. Okay, and then it is called a process. Okay, now during a process, the series of states through which a system passes during a process is called the path of the process. So initially when the system at an equilibrium state, it has a particular set of thermodynamic variables, that is particular pressure, volume and temperature. Now when the system is disturbed so that it goes through a process and settle for a new equilibrium state, it will have a new set of thermodynamic variables, that is a new set of pressure, volume, temperature and other thermodynamic variables. Now during this process, that is during this change from one state to another, its thermodynamic variables, that is pressure, volume and temperature, will continue to change until it achieves the final equilibrium state. So at every stage of this process, the state of the system will be denoted by a different values of by a different set of pressure, volume and temperature. So we will get a series of states during this process. That is, series of states means every state will have a different value of pressure, volume and temperature and other thermodynamic variables. Okay, so if we follow this series of states, what we will get is the the path of the process. Now to describe the process completely, we have to specify the initial and final state. That is, we have to state that at the initial state, what is the pressure, volume and temperature and what is the value of other thermodynamic variables, and same goes for the final state. And we also have to describe the path it follows. That is, during this process at every instant of time, at every stage of the process, what is the values of all the observable thermodynamic variables. We have to also specify that. Then the interaction with the surroundings. So how during this process, how the system interacts with the surrounding, that is, if there is an exchange of heat or if there is any other kind of influence, we also have to specify this. So here now during a process, we know that its thermodynamic variables of the a system changes. Now if we can plot how the thermodynamic variables of a system changes during a process, then the diagram we will get is called a integrated diagram. So through an integrated diagram, we can show that during a process how the thermodynamic variables of a system changes. Okay, so it will give us the plot of this change of the thermodynamic variables. Okay, so this property A, property B are basically the thermodynamic variables such as pressure, volume, temperature or other thermodynamic variables. So suppose this is this line shows the process. So initially the system is at state 1. Okay, this is the first equilibrium state. Okay, and it has this particular value of, this corresponds to a particular value of property A and property B, that is the thermodynamic variables. Now during the process, as you see, the property A and property B are changing. So every point on this line will give us a new states. Okay, so every point on this line will give us a new state of the system through which the system undergoes during a process. So if we follow all these states, okay, so what we'll get? We'll get the path of the process or process path. Okay, so finally it will settle for the states 2, which will be our new equilibrium state. Now what is quasi-static or quasi-equilibrium process? So when a process proceeds in such a manner that the system remains infinitesimally close to an equilibrium state at all times, then such a process is called a quasi-static process. So suppose here you see these are every point on this line, that is on the process path, denotes a different state, okay, through which the system undergoes during this process. So if every state is close to an equilibrium state, so the state 1 and state 2 are the ultimate equilibrium state, they are completely equilibrium state, but all these intermediate states are not an equilibrium state, but they might be very close to an equilibrium state, okay. So if through there is such a process that all the intermediate states are very close to an equilibrium state, then such a process is called a quasi-static or quasi-equilibrium process. Now the quasi-static process are sufficiently slow process, so that the process happens very slowly. So it allows the system to adjust itself internally so that the properties in one part of the system do not change any faster than the other part. So we know during a process there have to be some changes in the properties of the system, that is the changes in the thermodynamic variables, okay. So in quasi-static process, what happens that the process occurs very slowly. As a result, if there is some changes started to happen in one part of the system, okay, then the same change will occur at the same rate on the other part of the system, okay. So for example, suppose here what we have, suppose this is the system, that is suppose a gaseous system, okay, and over here we have some piston. So here so initially the piston was at this point, okay, now it is compressed, okay, very slowly. So as a result, the volume of the system, as you can see, has decreased. So initially this was the volume, now this is the volume, okay, and we know the pressure of the system will of course increase, okay, and so this shows the process in the on the indicator diagram. So initially the volume was V1, the final volume at the final states 2, the volume is V2. Okay, now the process is compression is very slow. So this will give this will denote a quasi-static process. So once now on the other hand, if the compression is very fast, then it will be a non-quasi-static process. So here every point or every stage during this process, every stage of the system during this stage or state of the system during this process will be very close to an equilibrium state. Whereas if the compression is done very fast, so suppose initially it was at state 1 the volume was V1, then it is compressed, the piston is moved very fast so that the compression happens very quickly. Then finally of course it will reach the state 2 such that its volume becomes V2, okay, then it will be called a non-quasi-static process. But here you see as the compression is done very slowly, its volume will decrease as well as its pressure will also increase, but the change in volume and the pressure throughout the system will remain somewhat equal at every part of the system. So as volume is decreasing, so the change in pressure will occur equally at every point, at every part of the system. Whereas in this case the volume is decreased suddenly, okay, decreased abruptly. Then the change in pressure will not happen equally. It will, the change in pressure is not, you can say, is not distributed equally throughout the system. So at some part the increase in suppose the pressure will of course increase, okay, at some part the increase in pressure will be high compared to other part. That is, suppose at this part pressure will remain at the initial value only, okay. So in such a case the state of the system, we cannot distinguish or cannot say at what point we cannot say what are the thermodynamic variables, how the thermodynamic variables of the system changes. Here we can, at every stage we can clearly see how the thermodynamic variables are changing. But if the process is very fast, which is a non-quantitative process, we cannot say how the thermodynamic variables of a system are changing. So that's why the process cannot be represented in a indicated diagram by a line. Here as you see, we have drawn a line, but here you see we have shown the process by a dotted line. Okay, so we cannot represent the non-quantitative process by on a indicated diagram. Here only the initial state and the final state are shown.